Share my screen. Okay. So what we are going to do today is one second. Cool. So in our last session, we have seen CNN model, right? So which stands for convolutional neural network. And I have asked you to go through the MNIST dataset as well. So MNIST dataset is something, it's a hello world kind of a dataset for image classification. So what is MNIST? We will discuss on it, and then we will, uh, build. So I have already built the CNN code, Python code. So I'll just walk you through each step one by one, and then see how does we apply CNN for the image detection. Okay. So MNIST dataset. So what is MNIST dataset? So before that, let's see what MNIST stands for. So M is one word and NIST is another word. So NIST means uh, National Institute of Standard and Technology, and M means modified. So before MNIST, it was known as NIST, and it's a US standard body, where 70,000 grayscale means black and white images of handwritten digits are there from 0 to 9. Okay, so what was NIST? First, let's see what is NIST. So it is a National Institute of Standard and Technology, and it was formally formed, I mean basically formed in early 1990s. And NIST, what they did basically, so they have collected the handwritten digit for, first of all, from various different people they have collected. And what was the purpose? I'll tell you. So they have collected handwritten digit for, first of all, postal code recognition, bank check processing, and optical character recognition. And this data, basically was collected as part of government and industrial automation effort in early 1990. And what's there in NIST dataset? So what was there initially? So it's basically the handwritten digits from 0 to 9, and written by many people, like thousands and lakhs of people. What they have, not lakhs, thousands of people. So they have collected, for example, they will come to me, Deepak, Raj, they will ask each of us to write some random number. So I'll write two. They will ask you to also write two, and then they will ask Raj also to write two. So the way in which we write two, all of us write two is different. So that's what. So they wanted to collect different ways of these handwritten digits from different people, so that they can basically use as part of government and industrial automation effort. And it was basically, so I'm talking about NIST. So images were of different size, different resolution. They were not properly formatted, not centered, and they were not uniform. So it's basically a very raw, messy, and real world handwritten data. So what happens with this kind of data? So for research and teaching, it had issue, right? So images had different size, digits were not centered, hard to train neural networks, and it's not beginner friendly, because early neural networks struggled with this inconsistency. So when there is no standard way of keeping each of these digits, because images of these digits were of different size, as they have collected raw data, right? So they have not done any post processing. Now what happens after this? So who modified NIST data? So a researcher whose name was, I believe, Yan Lee Kun. So this person and his team, they processed and cleaned the NIST data set. So as part of this cleaning, what they have done, so they have cropped the digit tightly. They have centered the digits in the image. They have, resized everything to 28 by 28 pixels. So this is a very important point. So every digit in MNIST is of 28 by 28 pixels. And they have removed the noise and inconsistency, and then they have standardized the format for ML. Now, after this modification, it's called as, you can guess now, right? It was called as modified NIST, which is also known as MNIST, after the modification that Yen and his team did. And it was first published in 1998. Now, as part of this modification, the final outcome or the final images that we got in this MNIST data set, so it is basically of uniform size. So when I'm talking about uniform size, it means 28 by 28 pixel. Each image is divided into 28 rows and 28 column, and each cell denotes 1 pixel. Then it is clean and centered digit. So every image was modified so that it becomes a cleaner image and a centered image. And it is actually, when they have done post processing, it is actually easy to load and use these digits. And with this cleaning of this data, it basically sets perfect data set for neural networks, back propagation, CNN, teaching, and creating the benchmarks basically. So it's basically perfect for the neural networks. So this is about MNIST history, and how the first NIST formed, and then how it is basically transformed into MNIST. Now, uh, now let's see what basically this data contains. So first of all, this data contains 70,000 grayscale. So when I talk grayscale, so it is black and white images. Okay, black and white images of 0 to 9 digits. Okay, and each image is 28 by 28 pixel. This I have repeated a couple of times now. And each pixel has value from 0 to 255. Okay, what does it mean? Let's say um, we have a number 9, something written like this. So now what was done is that it is basically divided into 28 by 28 pixel, means they will create 28 rows like this. 28 rows were created, dot 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 dot, I'll write. And then similarly 28 columns were also created around this image. So this is a black and white image. So 28 columns were also created. Again, let me write dot 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 here. Something like this. So this represents 28 by 28 pixels. Okay. Now what basically happens in this? So you can see each of these cells. So these small square which forms now represents 1 pixel or one cell. So this contains number from 0 to 255. 0 to 255. So 0 represents pure black, 255 represent pure white, and any number between 0 to 255 represents some shade of gray. Some shade of gray. So when this image is divided into these small cells, each cell there will be some number written. For example, here 28 will be written. Then here 114 is written. So some random number is written based on the resolution or based on the whiteness or grayness of that image in that particular area. So that's how uh, they have created this MNIST dataset. Okay, any doubt? Okay. So basically, it contains how many samples? 70,000 samples. 70,000 sample means there are 70,000 images of the digits from 0 to 9. 70,000 images. And whatever I am explaining here, it basically represent so one of the image. I mean any image. So out of 70,000, if you pick any image, this is how you represent that image, where you divide each image into 28 by 28 pixel, and each pixel contains value from 0 to 255 based on the grayness, whiteness, whatever you want to say, based on the grayness of that particular area. So that's how the all the images, 70,000 images were basically that's how they have divided these images, 70,000 images. Now, what we are doing here in our example CNN, so we will be using this MNIST dataset, and we will create one CNN layer. CNN, basically, we will create convolutional neural network, because CNN is basically used for image detection, and then we will detect the image in that dataset. Okay. Okay, now here is one more thing which I wanted to discuss uh, later on. Okay, but yeah, let me bring it later on only when we will be discussing the code. Okay, so let's go to the code. I have already created a code, Python code around it. So this is the code. Okay, now what we are doing, so as part of our normal, flow, we will be first of all using TensorFlow. So then TensorFlow is a library that we are using for the neural networks, right? And Keras, TensorFlow and Keras. So Keras is a part of TensorFlow. And this is basically to just print the TensorFlow version and the Keras version. Now, first step is to basically load and normalize the shape of MNIST data for CNN. Now, what we are doing here, so we are creating X train, Y train, X test, and Y test. And what we are loading this MNIST dataset. So how we are doing keras.datasets.mnist.load data, right? That's how we are loading it. And uh, next line, so I'll run this line after this explaining this line. So what we are doing here, we are training the shape of train data and Y train data. So train data, okay, here it's very important to understand the features and label also. So features here are basically images, right? So images are the inputs here, and label, that means the actual output, will be the digits from 0 to 9. Got it? So here features are images. That means input are images. So when I will print the shape of the X train data, means input data. So input is an image. So it will show like this. 60,000, 28, 28. Why 60,000? Because out of 70,000, it basically keeps 60,000 for training dataset and remaining 10,000 for testing dataset by default whenever we load the MNIST dataset. And 60,000 comma 2828, what does it denote? It denotes that we have 60,000 training data set, and each of this digit or each of this image is represented by 28 by 28 pixels. So that is why that's the shape will denote 60,000 comma 28 comma 28. That's what it means. Now when we talk about labels, so label will be denoted by 60,000. That means it is representing some digit, right? So I'm writing down randomly some digit, and this will be the label or the output. So the shape of that output will be, so it's just a one column, right? One label. So it will be 60,000. So let's try to run this program. Let's see what does it print. Why it is taking, okay, it is loading the libraries. You can see the shape it is printing. Input data का shape 60,000 2028, because by default it takes 60,000 rows for training data set and 60,000 labels will be there. So this is the shape of the data. Okay, now what is the next step? So what we have done, so we have uh, basically loaded the data. We have loaded the data. Now next step is to normalize the pixel. So one second. Yeah, so what we are doing as a next step is to normalize the pixel. So normalizing the pixel means, so the default value is in the data set, values are from 0 to 255, right? Now what we are doing, we will make the value between 0 to 1. So we are normalizing the value. So how we will normalize the value? We'll divide by 255. Before dividing by 255, we are changing the data type to float 32. So by default, the data type of the loaded data is uint8. So we from uint8, we have to change it. We have to change it to float 32 and then divide by 255. So what will happen? So every data basically this will be basically changed between value between 0 to 1. That's what it will do. Okay, now third step, adding the channel dimension. Okay, so what is channel? So that's what I wanted to discuss. Okay, so let's create 28 by 28 matrix. So that's how the matrix will be created, right? When we represent the image by 28 by 28 pixel, this is how the pixel will be created. Let's take any one cell. So we are taking this cell. So it will represent the value from 0 to 255, right? And if we want to represent it through, if we want to represent this value using matrix, so how we will represent? It will be a 2D matrix, correct? So first row will be represented by, let's say, any random number. Any 28 numbers will be there. Like this, it will represent, which represents the first row in this division that we have done. Then second row will be represented by some other 28 numbers, something like this. And similarly, this will go on till 28 rows, right? So this is how the data is represented. So here you can see, so this particular row data is represented by this row. Okay, guys, can you hold on, please? I have someone at gate. 1 second. Okay. So this is how the data is represented, and you can see this inner list, each list represent one row in the data. So first row, second row, third row, and so on. Now, when we create channel, what will happen? So when we create channel, so what will happen to this data? I'll tell you. So this data we will convert into, we will add one more dimension here. So when we will add one more dimension, so data will somewhat look like this. So every value will go in a separate list. And why we are doing that? I'll also tell you that also. 33, 445, and so on. So each value, whatever was there, will go in a separate list like this. Okay, like this. Why we are doing that? So you can see this has gone in a separate one-dimensional array or separate list. This means we are adding one more dimension of one more dimension in the data. Why we are adding this one more dimension? So for black and white images, we say that we can add one channel. For colored images, if we would have been having colored images, we would be adding 3 channels. So 3 channels means each channel represent RGB value. R one, one channel represent R, another G, and another B. So any colored image will be converted using 3 channels. Now here we have added one more dimension here. So we are adding just one channel in black and white case, right? Because that's how the data will be passed to convolutional neural networks. That's the standard way of passing the data, by adding the channel so that it knows whether the incoming data is a black and white data or a colored data. Okay. Now let's say if it would have been a colored image, so their channel will be 3 channels, right? So in that case, what would have happened? So it will be like this, and each value will be converted into, so if we are adding one more dimension, so how we would have done? So we would have added like this, and so 3 channels will be there, so 3 values would have been added. Now what does it mean? What does we mean by 3 value? So you know, right? Colored image is represented by RGB values. So this represent, first value would have represented R, G, B, because any color in this word is represented by RGB value, and this is the RGB value for this particular color of the pixel or this pixel's color. So यहाँ पे let's say this is representing this data, this cell is representing this data. So it might be of some color, right? So what is that color? So we represent that color by this RGB value. Means we have been using 3 channels here in case of colored images. So this is how these 3 channel basically means. So 3 channel represent RGB, which represents colored pixel. But here in this case, we are using just black and white picture. So that's why we are using just one channel here. So each pixel is converted into one channel. So usko convert, how did we convert it? We just have added one more dimension, or we have just enclosed each number into one square bracket or one list. So that's how we change or add channel dimensions. See, in this state, in this step, we are adding one channel dimension. So instead of 28 by 28 matrix, it becomes 28 by 28 into 1. It becomes 3D now. From 2D to 3D it become. Okay. And if any, okay, so any matrix, if it's a 2D or 3D, how do you know? So just check the starting, square bracket. So here, one square bracket, two square bracket, three square brackets are there. So this is a 3D array or 3D matrix. Here also one square bracket, two square bracket, three square brackets are there. So this is again a 3D array or 3D matrix. Like this, we can quickly know about the nature or the dimensionality of the matrix. So that's what we have done here. So we have added channel dimension. Okay. So how do we add this channel dimension? So we will be, what we are doing, we will be assigning, we will be taking the xtrain data and assigning it into the same variable. And now how we are doing? So we will be using 3 ellipses and then np dot new axis. So new axis, what it will do? It will add one more axis, new axis. And these 3 ellipses, this in NumPy, it's a shortcut used for slicing array when you don't want to write all dimensions explicitly. So it basically means that keep all existing dimensions unchanged and just add new dimension here to represent the channel. So that's how we are doing. We are adding one more channel. So if I would be running this particular, print statement, it will print these values like this. Okay. So what we have done so far, we have taken images. So train and test split is already coming when we are loading the data set. 60,000 train data set, 10,000 tested data set, and for each pixel we are adding one more dimension which represents the channel. And if it would be a colored image, we would be adding three channels instead of one channel. But it's a black and white image, in consideration, so we'll be adding just one channel. So we have normalized. Okay, what we have done so far, let's see. We have loaded the MNIST data set. Then we have normalized the pixels. And after that, what we have done, we have added one channel dimension. That's what we have done so far. Okay. Now, next step, we'll be creating one CNN, convolutional neural network. How we will be doing that? Let's see that now. Okay. So what we will be doing, we will be using keras.sequential. So sequential means we'll be creating sequential layers. First of all, we'll be creating input layer. So input layer we have created, and it will be of shape 28 by 28 into 1. So what it represents, so we'll be creating the shape as 28 by 28 because each digit, image is the input here, right? So each image basically is represented by how we represent 28 by 28 pixel, right? That's how we represent the image, and image is the input here. So that's why shape we have given 28 28, and later on we have added one channel here, right, in the black and white image. So that's why we have made it as 28 28 comma 1. So this is the input layer we have decided. Now you remember in last lecture we have discussed about convolutional block. flattening of the layer, and then FC blocks, three main blocks, right? So first, we'll be creating two convolutional blocks. So what are these? These are convolutional blocks. Okay, now what we are doing in these convolutional block, let's see that. So convolutional block, let me just take a recap. So convolutional block consists of convolutional layer, then we pass it to activation layer. So let's consider that we are applying ReLU on that, and then finally we have pooling layer, correct? So this is known as one convolutional block. Okay, now what we are doing here in this case, so we have created two convolutional blocks here. So in first convolutional block, we are using 32, 3 by 3. What does it mean basically? So it means that boss 3 by 3, first of all, let's see what is 3 by 3. So it means that boss create a 3 by 3, look at a small 3 by 3 part of the image and find pattern. And it's like a 3 by 3. Okay, let's consider that as a 3 by 3 frame. So we will be, using this 3 by 3 frame here, and then we will slide it again 3 by 3 ka frame to next step, and then next step. So 3 by 3 frame is basically used to scan the image, whole image of this digit. So, and how many ways we will be doing? We will be doing it in 32 ways. So what does it represent? It represent that create a 3 by 3 frame or 3 by 3 filter, I would say. 3 by 3 filter, 3 by 3 filter. Uh, and slide over the image. And what is the basic intention of doing it? So as we know, right, in convolutional layer, we basically detect edges, corner, texture, and shape about the image. So it basically it is used to basically find patterns in the image. So 3 by 3 means 3 by 3 ka frame we are making, and then we are sliding on each part of the image so as to find the pattern in the image. And in how many ways we have to do that? In 32 ways. So that this first parameter 32 represents that. So 32 is basically number of filters or kernels, we basically say filters or kernels. So we will be using this 3 by 3 filter in 32 ways to scan through the image. It's like a 32 different pattern detector. Okay. So this is what is represented by this first convolutional block, what we are conv2D when we are using, right? And we will be using activation layer. So here you can see that ReLU is the activation function used, right? So that's what we are mentioning here. And now layers dot max pooling 2D 2 by 2. Now what does it do? So pooling layer ka what was the intention of using pooling layer? First of all, compression, right? We used to do compression of the image. Compression by reducing feature map size, right? Remember what we have discussed in the last session. Then keep most important feature or keep most important information intact. And then third will be improve speed and reduce the overfitting, right? So basic usage of applying pooling layer is the compression. Okay. How do we do the compression here? So we are mentioning layers dot max pooling 2D 2 by 2, 2 comma 2. Okay. What does it mean 2 by 2 or 2 comma 2? So it tells that we take a 2 by 2 region. So for example, a pixel, so this image is represented by pixel. We will be taking 2 by 2 ka area. So 2 by 2 area in this image will contain, 4 cells, something like this, 4 values, right? So divide this whole image into 2 by 2 ka area or 2 by 2 ka matrix, and out of these 4, so it will contain 4 value, each 2 by 2 ka, right? 4 values will be there, correct? Now what it is telling, that out of these 4 values, um, okay, let me write down. We take 2 by 2 region and replace it with just one value. And what value will it be? The maximum value, whatever is there. So it means that. So that's how we are applying pooling here. So we are compressing the image now. So first we have, detected the pattern in the image by using convolutional layer. Then we have applied the activation layer, and then we have applied the pooling layer. Pooling layer mein we are doing the compression, and how we are doing the compression? We take 2 by 2 region and replace it with just one value, which is the maximum value. So this we are doing in one convolutional block. Similarly, in this example, we'll take two convolutional block. In the second convolutional block, instead of doing it in 32 ways, we are just adding more, more smartness or more kernels. So instead of, in doing 32 different ways, in the second convolutional block, do it in 64 different ways. So we have used two convolutional block in this case, these two blocks. Now, after using convolutional block, what we will be doing? So we are using one flattening, what you say, flatten layer, right? कैसे करते थे हम? Input layer, then we have convolutional blocks. So this is input layer or input coming. Then this is convolutional block. So this is convolutional block 1. This is convolutional block 2. And after that we add basically ये flattening layer we used to do, which is known as a transition state, right? Flatten layer. What we used to do in flatten layer? So we convert 2D or 3D feature map into 1D vector, where there is no weight associated with that, and there is no learning happening there. So output of this stage is basically to transform. It basically transforms extracted feature into decision ready format. So flattening layer के बाद finally what we will do? We will create FNN, right? FNN layer, normal feed forward network, and then finally the output layer will be there. This will be the flow that we are talking in this particular example. So यहाँ पे flattening, how we will do the flattening? So layers dot flatten. So this is the flattening we are doing. Then we are using FNN. So FNN में what we are doing? Hidden layer we are adding. So this is FNN. यहाँ पे हम we are adding hidden layer. And how we are adding hidden layer? So we are adding 128 neurons, and activation function that we are applying here is ReLU. So FNN hidden layer is there, and this is flatten layer. And what is this? These were convolutional blocks. Convolutional blocks. What does it contain? Convolutional layer plus activation layer plus pooling layer, correct? Pooling layer. So FNN layer. So यहाँ तक we have came till now, till this point. And dropout kya? I'll explain you what is dropout. Before that, let's see this output layer. So this is final output layer, right? So output layer में it is telling that keep 10 neurons. Why 10 neurons? Because output will belong to any of the 0 to 9 digit, which are total in 10 digits, right? So that is why 10 neurons we are keeping in output layer, and activation function soft max we are applying because this kind of a classification problem. And this is how we have built this whole neural network CNN ka. Now let's talk about this dropout. Dropout 0.3, what does it mean? So when we talk about dropout, yeah. Okay, so what does dropout 0.3 means? So dropout 0.3 means it is telling that randomly turn off 30% 30% neurons during training to prevent overfitting. So why it is turning off 30% neurons during training is to prevent neurons to be dependent on each other, and to make sure that every neuron must learn everything. So when we don't use the turn off process, so each neuron will be dependent. So all the neurons will be dependent on some of the neurons. But when we turn off the 30% neurons, it makes sure that every neuron will be learning at the same intensity. So this is the purpose of doing the dropout. So this is how we are building this CNN layer. Okay, now next step again. So this will be the common steps. What we are doing here, model.compile. We are compiling the model. We are using optimizer as Adam for adaptive gradient descent. Loss we will be calculating. So this is a classification problem. So cross entropy will be using. So sparse categorical cross entropy. Metrics will be the accuracy. Then we'll be using model.summary. And then we are doing fit, means we are training the model. So how we are doing the training, model.fit, X train and Y train data we are giving. And from the training data set, keep 10% as the validation data set. Total epochs we are doing 5. Batch size is 32. So it will be taking the 30 to 32 batch size, samples in each batch. And then we are evaluating the performance of the test data, right? And then these are the steps for prediction on the new image. So new image, okay, let me show you the images also, MNIST image. So let's say, let me add. So this is, you can see on the screen, this is number 4. This is number 4 from the MNIST data set. Let's open some other. This is number 2. Similarly, this is number 0. So these are the numbers that are present in the MNIST dataset. And what I have done, so I have downloaded this MNIST dataset, and randomly I have taken one number which I have provided as input. So what I am providing here to predict on new image. So I have saved some of the images in this particular folder, and I am providing this particular image as the input, and I am asking basically my model to detect this image. So what is the image? This is the image of number 7. Okay. So let's try to run this and see if it runs fine. See, it has started training the model. Epoch 1 is going on. It takes some time because it's a CNN network. Let's see what does it produce. Sometimes it predicts wrong also. You can see in each epoch it is calculating the accuracy loss also, right? Accuracy 94% in the first epoch, 98 in the second epoch. You can see how time consuming the training is for these 70,000 data set, because it is training on images, not on some random text, right? See, it has predicted the digit here. It has predicted the digit as 7. And that's what we have passed to this model as the new data that we have provided. So uh, you can, try to understand more on MNIST dataset on your own as an assignment. Try to dig deep into what MNIST dataset is all about, and how does the basic CNN neural network understands the data, and how do we basically apply different kind of layers in creating the CNN, convolutional neural networks when we create it. And I wanted to make sure that instead of focusing on writing the code, I would like to spend more on explaining the code. So that's why I have used this pre-written code. So I believe now you might be understanding what each of these line means, and how the CNN is basically working here. So any doubts before? I think we are done with the neural networks. I don't want to dig more into the neural network, because that's not the primary agenda of this course. And from next session onward, I'll be starting generative AI sessions. So stay tuned for generative AI session, because that will be really very interesting, and that is something what is latest happening in the market. And I'll be covering all the latest topics and all the latest use cases, whatever I can cover up. So please make sure that you guys are attending the classes regularly from the next lecture onward, because I may not be recording those sessions because of copyright infringement. But in case if I'll record the session, I'll share it with you and then probably delete it after 2 3 days. So instead of that, so make sure that you are joining in the sessions. So we'll start with generative AI first. Then we will go into the concepts of NLP. Then we will go into the concepts of LLM. Then agentic AI and what are agentic AI and AI agents. And then we will be discussing on different frameworks for agentic AI, like LangChain, Crew AI, and LangGraph. And if time permits, I'll also try to cover OpenClaw. OpenClaw is something recently launched into the market, and I have also taken a recent webinar on OpenClaw. So let's see if we can get some time to discuss on OpenClaw also. So yeah, that's about it for neural network for today. Any doubt before we wrap up today's session? Raj, Deepak, Sarthak, any doubt?
No, Carlos, no doubt. How are you?
Okay, cool. Okay, then we'll meet up in next session then. So I'm not sure about tomorrow's session. It's tentative. So I will be stepping out with family tomorrow. So if I'll be able to come back on time, I'll be taking that session. If not, then I will cancel tomorrow's session, and then we'll start afresh with generative AI from next session onward. So I'll just update by tomorrow morning. Cool. Thank you, guys. That's it for today's session. Have a nice day ahead. Thank you.